Okay, Assalamualaikum warahmatullahi wabarakatuh. A very good day, everyone. So, I am Dr. Emilia. So, for today, I'm going to explain on the chapter 9. This is our final topic for Engineering Mac 4 BFC 32403. So, on topic 9, we're going to discuss on the partial differential equation or PDE. Okay, basically, in this chapter, you have three subtopics to be covered. Okay, which is the parabolic, hyperbolic, and also elliptic. Since we are having a constraint, or we are facing a constraint on time, okay, we have decided to just focus on the parabolic equation, which referring to the heat equation. Okay, in the heat equation, you're going to have two methods to solve or to estimate or to approximate the value of a heat towards rods or a steel rod. Okay, either using the explicit finite difference method or Crank-Nicolson method, or also known as implicit method. Okay, in this part 1 of my video, I'm going to explain on the approximations of a heat equation or heat value towards a rods or steel rod, okay, using the explicit method. Okay, so what are the difference between ordinary differential equation and partial differential equation? So we can look at the equation itself, or that normally for the ordinary differential equation, you will have a function of fx. Okay, in the ordinary differential equation, you usually have one independent variable which refer to the x value, and also you can have one or more dependent variables. Depends on the axis. You can have y and z and so on as a dependent variables. Okay, so the functions or the derivative of function of the fx also can be written as a y prime dy towards x. Okay, so those are the example on how we can recognize that the equation is ODE or PDE. So this is ODE equation. Yeah, you can see here ODE only have one degree or one derivative levels, one derivation. Okay, single level. So however, for the partial differential equation, the equation normally been written like this, a function of u towards the independence variable of the function x or y. Okay, this is an example on how the equation to be written. Okay, so you can see here, okay, for all partial differential equation, they have the power 2 of the derivative over here. Okay, so for partial differential equation, you can have two or more independent variables and also one or more dependent variables. Okay. Okay, how to recognize the classification of partial differential equation? So PDE is an equation involving function of a multiple variables and their partial derivative. Okay, their classification can be recognized by b squared minus 4ac. Okay, you can refer to the module on the page 215 and on what is b, a, C, and so on. So basically A, B, C, and so on, they are the constants of function of x and y. Okay, so for you to classify or to categorize the function, either it's parabolic, hyperbolic, or elliptic, so you can look at the b squared minus 4ac value. If the b squared minus 4ac value is equal to 0, meaning that you are dealing with the heat equation. Okay, so the equation will be formed like this. Okay, if you get the value of b squared minus 4ac is less than 0, meaning that you are dealing with the wave equation or the hyperbolic. Okay, so this is the form of the equation. You can spot the difference over here between parabolic and hyperbolic at the second function over here. Okay, for the hyperbolic you will have d squared u over dt squared. Okay, but for the heat equation you only have the first level of derivation. Okay, and for the elliptics, the value of b squared minus 4ac will be less than will be less than 0. For hyperbolic is more than 0, and elliptic is less than 0. Okay, and the value can represent either Laplace or Poisson's. Okay, depends on the function or the equation formation. Okay, so this is for the Laplace. Okay, you have three variables here. Okay, y, u, and also x. Okay, and this is for the Poisson. Okay, but however, for this course, you only going to focus on the heat equation, whereby the value of b squared minus 4ac is equal to 0. Okay, so for heat equation, there will be two methods, either using the implicit or explicit method to do the approximation. Okay, in my first video on chapter 9, okay, I'm going to explain on the explicit, okay, for heat equation. Okay, so as I mentioned before, a heat equation or a parabolic equation is when the value of b squared minus 4ac is equal to 0, and this is the heat equation, the form of the heat equation. Okay, you have to remember. Okay, for heat equation, d squared u over dx squared minus 1 over c squared, and this is the alpha. Okay, times by du dt must be equal to 0. Okay, when it's equal to 0, meaning that this is the parabolic equation. Okay, so what are we going to do in this chapter is actually, okay, let's say you've been given one steel rod. Okay, so this steel rod will be heated, okay, at the boundary. Okay, so we want to know after a certain time, okay, so what will be the heat value, okay, at certain point towards the steel. Okay, so how much ataupun what is the temperature, okay, for the steel, okay, at certain point or at specific point, okay, throughout the steel after a certain time. Okay, so this is what we're going to approximate, okay, on chapter 9. Okay, so there are few things that you have to look before you can do the approximation. Okay, you need to understand on what are the boundary condition on the start point, and also what are the boundary condition at the end point. Okay, the boundary condition meaning that what are the value of heat, okay, at the two ends of the steel rod. Okay, so you need to know first. Okay, because if you don't know, you cannot solve the equation using explicit method. Okay, therefore in the explicit finite difference method, the heat equation at the point xi tj. So basically for xi, okay, x is the x-axis. Okay, x-axis meaning represent the length of the rod. Okay, and for tj, okay, t is the y-axis. This is the y-axis. Sorry. Okay, I draw. Okay, so this will be your y-axis. Okay, this is t. Okay, y-axis represent by time. Okay, so basically this is your initial, or when the time is 0 second. Okay, you have a steel rod with certain temperature, and you have to know, or you have to determine, okay, what are the temperature at specific point throughout this steel rod. Okay, so at y-axis, okay, let's say after certain time, let's say after 1 second or after 2 seconds, okay, what are the temperature, okay, at the specific point on the steel rod. Okay, those are the value that you're going to determine, or you're going to approximate using the explicit method. So these are the values that you want to approximate. Okay. So before you can do further on the analysis to approximate the value or the temperature on the steel rod after certain time period, okay, you have to first recognize the heat equation given by the question. Okay, you must first remember in the general formula of heat equation, this is the formula. Okay, du dt, okay, for the function of x and also time, length and time. Okay, c square d squared u over dx square. Okay, this is the general formula for heat equation. Okay, for you to do the approximation, you can use forward time central space, okay, or FTCS, finite difference, okay, method, using this formula to do the approximation. Okay, this is the standard FTCS formula, okay, or finite forward time central space formula. Okay, this formula shows that if you want to find the value at I j plus 1 must be equal u I j plus lambda. Lambda, this is the coefficient, okay, for the heat. Okay, the lambda value can be calculated using this formula, okay, which is lambda is equal to delta t, the difference of time, divide by delta x square, the difference or the interval at x axis, times 2. Okay, so this is the lambda or the coefficient of the heat equation. Lambda times u I plus 1j minus 2 uij plus ui minus 1j. Okay, this is the general forward time central space formula that you're going to use to do the approximation for the temperature value of the rod at certain point. Okay, so if we translate or illustrate this formula into visual illustration, this is what you get. Okay, from this equation, I transfer it or I illustrate it in a visual, okay, visually. So basically, the yellow box over here, the value over here is the value of u I j plus 1. Okay, I meaning that this is the center. Okay, this is center. So we assume that the coordinate at the center is I. Okay, so j plus 1, j is at y-axis. Okay, this is y-axis. Okay, j plus 1, this is j. Your first, the first initial time at y-axis is j. Okay, a time after the initial time is the j plus 1. This is the j plus 1 coordinate. Okay, so this is j plus 1 coordinate. This is j plus 1 in y-axis. Okay, but in the x-axis, okay, the central point we consider as the I. Okay, the point or the coordinate behind or at the right left of the central point is I minus 1. Then the coordinate in front or on the right of I is I plus 1. So this is I. This is I minus 1, this is I plus 1. This is how we define the coordinate of the point on the road using FTCS method. So meaning that for you to calculate the value in the yellow box, okay, you need to use the three values over here at bottom or at the initial data, initial road condition, okay, to get the value over here. Okay, usually if we are using explicit method, we will have the value at the boundary, okay, the temperature value at the boundary, and also we going to have the initial temperature value at time at t equal to 0 or at J over here lah. Okay, maksudnya jika kita nak menggunakan kaedah explicit, biasanya kita akan diberi nilai-nilai pada boundary ataupun temperature value pada kedua hujung rod, okay, dan juga temperature value awal ataupun initial temperature value for the rod at T equal to 0. Okay, you akan diberi nilai-nilai tu. So bila you you ada all this value, okay, so meaning that you can calculate the value at U I J plus 1 over here. Okay, so jika this one rod, kalau let's say you ada this rod, okay, at T equal to 0, okay, 0 second, so pada keadaan yang awal, initial, you tahu berapa nilai haba pada kedua-dua hujung, okay, yang ni kita panggil sebagai boundary condition, dan you juga tahu berapa nilai haba pada initial T equal to 0 at certain point on the road. Okay, katalah road ni panjangnya 1 meter, okay, so saya ada katalah saya ada 4 lokasi yang saya dah marking. Okay, so nilai haba pada keempat-empat lokasi ni saya tahu. Okay, saya mesti ada value dia. Okay, so initial value you must have. Okay, and also the boundary condition value, temperature at the boundary also you need to have if you want to use the explicit method to do the approximation. Baiklah, sebentar lagi saya akan sambung dengan satu example on explicit method yang akan menunjukkan the full solution on how you can estimate or approximate the heat value on a road after certain time of period or after certain period of time. Okay, so I end up this video first and then I will continue with my second video on chapter 9 to explain on the example for explicit solution. Thank you.